Prof. Pengju from Zhejiang University. Okay, so it's my great pleasure to introduce Prof. Pam. So Prof. Pam get a PhD from Tokyo Institute for Technology, and then he worked as a postdoc in Riken in Japan. Then at that time, so Prof. Pam and I had collaboration. Then we knew each other. Then after that, Prof. Pam moved to Zhejiang University. He was an associate professor and then promoted to full professor. Then I visited Hangzhou, Zhejiang University. So I really appreciate your great hospitality when I visited Zhejiang University. Thank you very much. Okay, so today, Prof. Pam will give a talk about the stereocomplex crystallization of polymers. So everyone, please join me to welcome Prof. Pam. So, Pengju, can you start?
Okay. Can you see me, Sigrid?
Yes.
Okay. Good morning, everyone. Thanks for the kind invitation of Professor Goto. I'm Pengju Pan from Zhejiang University. I'm very pleased to have this opportunity to talk in the NTU Chemistry virtual seminar in the special period of COVID-19 epidemic. Today, I will talk about our recent study on the stereocomplex crystallization and the stereocomplex material of polymer. All of this talk. First, I will give a brief introduction for the stereocomplex crystallization. Then I will talk about the crystallization behavior of stereocomplex polymer and the control of stereocomplex crystallization. These two parts focus on how to crystallize and how to control the crystallization of stereocomplex polymer. In the fourth and fifth part, I will talk about how to use stereocomplex crystallization to make the material. I will focus on the polymer elastomer hydrogel micelle prepared from the stereocomplex crystallization. As we know, many polymers are assembled crystalline. Crystallization gives the polymer material good physical properties such as high strength, modulus, and high heat deformation temperature. The general crystallization occurred in the homopolymer system. However, the different polymer can also co-crystallize in the same crystal lattice if they share the very similar chemical structure. A general co-crystallization is a stereocomplex crystallization between the polymer pair with the different chemical structure, but complementary configuration. The typical polymer that can co-crystallize in stereocomplex are the isotactic and syntactic PMMA, L and D polylactic acid. Recently, polymer chemists also reported many new stereocomplex polymers, such as the CO2-based polycarbonate and aliphatic polyester. The well-known stereocomplex polymers are poly-L-lactic acid and poly-D-lactic acid, PLLA, and PDLA. They can form the stereocomplex crystal in the blend or block polymer. Both the PLLA and PDLA are represented as a typical barrel-based and barrel-degraded polymer. Their monomer lactic acid can be prepared by the fermentation of biomass. Let's see the crystal structure of steel complex of PLA and PDLA. There are two polymer chains in the crystal unit cell. One is the PLLA, the other one is the PDLA. Because the helical direction of these two polymer chains are different, they can form the dense packing in the crystallitis. This unique structure gives many unique physical properties for the steel complex polymer. For example, the melting point and heat deformation temperature of steel complex PLA is about 50 degrees higher than the homocrystalline material. Steel complex material also have better chemical resistance. The steel complex material of PLA can't be dissolved in the many solvent that can dissolve the homocrystalline PLA, such as chloroform, THF, and DMF. It's just dissolved in the very special solvent, such as HFIP. In summary, the physical property of homocrystalline PLA are similar to the common plastic like PP and PS, whereas the physical property of steel complex PLA are similar to the engineering plastic like PET and nylon. So it's possible to change the material property of PLA from the common plastic to the engineering plastic by changing the crystal structure. Unfortunately, not all of the PLA and PDLA blend can easily form the steel complex crystal. In the crystallization process of PLA and PDLA mixture, there is a competition between two crystallization processes. One is the homocrystallization of PLA or PDLA. The other one is the co-crystallization between PLA and PDLA. We have found the molecular weight is a key factor for this two crystallization process. For the low molecular weight PLA and PDLA, they have the fast crystallization rate and mainly form the steel complex in the common cooling and heating process. However, when the molecular weight of PLA and PDLA are higher than 50,000, the blend mainly forms the homocrystal in the cooling and heating process. The crystallinity of steel complex is very low. To understand the crystallization behavior and mechanism of steel complex polymer, we studied the crystallization behavior of PLA and PDLA with a low and high molecular weight. For the low molecular weight system, molecular weight of PLA and PDLA are about 20,000. With a low molecular weight, PLA and PDLA are also thermocrystallized in the temperature range from 120 to 200 degrees C. We just observe the melting peak of steel complex crystal in the DSC and the diffraction peak of steel complex in the wax dependent. This means the low molecular weight blend lacks the steel complex crystallization. However, high molecular weight PLA and PDLA blend shows a much different crystalline structure from the low molecular one. Your used high molecular weight blend, molecular weight of PLA and PDLA are higher than 80,000. We crystallized the blend in a wide temperature range from 80 to 100 degrees C. When the crystallization temperature is lower than the melting temperature of homocrystal, we mainly observe the melting peak and the diffraction peak of homocrystal in the DSC heating curve and the wax pattern. When the crystallization temperature is higher than the melting point of homocrystal, homocrystal can't be formed, and we just see the melting peak, the diffraction peak of steel complex. Linearity of steel complex changed little with temperature in this wide temperature range. This means the high molecular weight PLA and PDLA blend mainly form the homocrystal in the crystallization temperature range of homocrystal. Because both the stereocomplex and the homocrystal can be crystallized in the temperature range from 80 to 160 degrees C, we are curious about the competition between these two crystallization processes. We studied the crystallization process of the blend at 160 degrees C by the wax D. In the crystallization process, we first observe the diffraction peak of stereocomplex and then observe the diffraction peak of homocrystal. The intensity of homocrystal increased more significantly than stereocomplex in the later stage of crystallization. We explain the crystallization of high molecular blend. From this result, the stereocomplex crystal first formed in the crystallization process. The formed stereocomplex crystal can work as the crystal link and retard the mobility of linked polymer chain. On the other hand, it is reported that the stereocomplex crystal can work as the nucleating agent of homocrystal. Therefore, homocrystal are kinetically favored in the later stage of crystallization. However, because of very low stereocomplex content, the effect of stereocomplex on the following crystallization process is not so significant. It just affects the crystallization kinetics, but not the crystalline structure of the homocrystal. We expect if we can extend the content of stereocomplex, it will have a more significant effect on the following homocrystallization process. So it can also induce the formation of some specific homocrystalline structure. And this was confirmed in the medium molecular weight blend. Molecular weight of PLA and PDLA is a medium molecular weight blend about 40 degrees C. Medium molecular weight blend sample shows very special crystallization kinetics and crystalline structure. For the melt quenched amorphous sample, we see two crystallization peaks in the heating process. This is a typical behavior of fractional crystallization. However, the other blend just show one crystallization peak during heating. For the blend crystallized at 80 degrees C, the medium molecular blend shows the diffraction peak of homocrystal at the different diffraction angle. To further confirm the unique crystalline of medium molecular blend, we crystallize the sample at a wide temperature range from 60 to 140 degrees C and study the heating process by DSC and measure the crystal structure by XRD. For the blend crystallized at the temperature lower than 100 degrees C, we see an additional crystallization peak in the heating process. This suggests the crystallization is constrained in the isothermal crystallization process. For the sample crystallized at the low crystallization temperature, the diffraction peak shifted to a higher angle compared to the common homocrystal. This means the medium molecular blend forms the unique homocrystal under this condition. To recognize this unique homocrystal structure, we enlarge the wax XRD pattern and compared the XRD pattern with the reported polymorpha of PLA, including the alpha, beta, and gamma form. We confirm this crystal belonging to the beta crystal. Beta crystal is one of the polymorpha of PLA, but it is quite difficult to be attained. We also propose the crystallization mechanism of the beta homocrystal. is a crystallization process. The high content of steel complex crystal are first formed is a crystallization of the medium molecular blend. This steel complex crystal can work as a cross-linker and retard the regular packing of polymer chain in the following crystallization process. The cross-linking effect of steel complex can have a stretching effect on the polymer chain and induce to form the beta homocrystal with a more extended polymer conformation. Since beta form is a more stable form of homocrystalline structure, we investigate its phase transition during the heating process. We first crystallize the sample at a low crystallization temperature to get the beta form crystal, and then measure the in situ FDR XRD pattern in the heating process. We first observe the further crystallization of beta form and the homocrystalline structure. Of the homocrystalline structure is a temperature range at around 130 degrees C. And we see the transformation from the beta to alpha homocrystal with heating to about 150 degrees C. This phase transition is a melt recrystallization process. We can further observe the melting of alpha, a homocrystal, and steel complex is a further heating process. After understanding the crystallization behavior of the blend with different molecular weight, we return to the high molecular weight system. The commercial available PLA and PDLA all have the high molecular weight, and only the high molecular weight sample have the good mechanical property and process ability. Therefore, the high molecular weight system will be more important for industrial application. As we talked before, high molecular weight blend like a homocrystallization and don't like a co-crystallization. It is still unknown why high molecular blend don't like co-crystallization. We think there are two possible reasons. One is that the mixing of L and D polymer may not be completely homogeneous in the melt. Somewhere has more PLA chain and somewhere has more PDLA chain. This PLA and PDLA rich domain would crystallize in homocrystal. Because the mixing level can be improved by increasing the interchain interaction between the D polymer, we believe enhancing the interchain interaction can improve the steel complex crystallization. On the other hand, compared to the conventional homocrystallization, steel complex crystallization needs an alternative packing of PLA and PDLA. It has a long diffusion pathway and is more controlled by the chain diffusion in polymer crystallization. So we believe enhancing the diffusion ability of polymer chain can also improve the steel complex crystallization. Based on this consideration, we tried several methods to improve the steel complex crystallization of high molecular weight system. This method including the use of specific nucleator, a block polymerization, incorporation of non-covalent bonding unit in the chain terminal, blending with hydrogen bonding component, miscible blending, control of topology structure. This fourth method was to improve the interaction between L and D chain. In the block copolymerization, we linked the L and D block by the covalent bond. Instead of the covalent bonding, the interchain interaction can also be improved by using the non-covalent bond, such as hydrogen bonding in the chain terminal. In these two methods, we improve the steel complex crystallization by improving the chain diffusion ability or decreasing the chain diffusion length. Due to the time limitation, I will only introduce the non-covalent bonding method in this talk. We use the multiple hydrogen bonding to enhance the interaction between the L and the D chain. Multiple hydrogen bonding are very common in the nuclear base of DNA and RNA. In our study, we choose a well-used multiple hydrogen bonding unit, UPy. This is the chemical structure of a UPy unit. Two UPy groups can form the fourfold hydrogen bonding interaction. Strength of this hydrogen bonding is close to the covalent bond. In order to introduce the UPy unit to the chain end of PLA, we synthesize a hydroxyl functionalize the UPy and use it to initiate the reopening polymerization of lactic. This gives the polymer mono-terminated by UPy. On the other hand, we synthesize the tetrachelic PLA and three-armed PLA terminated by hydroxyl group and then converted the end group to UPy. This gives the polymer with 2 or 3 UPy terminals. We then mix the UPy terminated PLA and PDLA and crystallize them at a different temperature to study the effect of terminal hydrogen bonding interaction on crystallization structure. We compare the XRD pattern with a non-functionalized PLA and PDLA blend. By comparing the XRD pattern of the sample crystallized at the same temperature, we can see the content of stereocomplex increase after the introduction of UPy unit. But this effect is not so significant in the case of polymer containing one UPy group because 2 PLA and PDLA chain can also link together by the UPy hydrogen bonding interaction. Effect of UPy hydrogen bonding on crystalline structure become more significant for the polymer containing more UPy unit. For example, for the polymer, for the PLA and PDLA blend with 3 UPy unit, they only form the stereocomplex crystal at a high crystallization temperature. The content of stereocomplex crystal is much higher than the common blend without the UPy hydrogen bonding. This means the stereocomplex crystallization ability can be enhanced by improving the interchain interaction. After knowing how to control the stereocomplex crystallization, we further studied how to prepare the high-performance material by stereocomplex crystallization. Compared to the common homocrystallization, stereocomplex crystallization have several special features. First, stereocomplex crystallization has a strong driving force. It is driven by the hydrogen bonding interaction between L and D polymer chain. Therefore, stereocomplex crystallization would have stronger crystallization ability than homocrystallization. Some non-crystallizable polymer can become crystallizable through stereocomplex crystallization. Second, because the polymer chain packed more densely in stereocomplex crystal, they will have high crystal module and strength than the common homocrystal. Third, stereocomplex crystallization needs an alternative packing of 2 different polymer chains. The formed stereocomplex crystallization can function as physical cross-linker in the material. Therefore, stereocomplex crystallization would have better reinforced effect on the polymer material. We use the stereocomplex crystallization to reinforce the elastomer and hydrogel. In the first case, we use the stereocomplex crystallization to reinforce the ABA tree block polymer. A is the hard block and B is the hard block it is either PLA or PDLA. B is a soft block, mid block. We use a random copolymer of caprolactone and the valorolactone block. We also mix the PLA tree block and the PDLA tree block polymer to prepare the Stereocomplex elastomer. From the wax XRD pattern, we can see the homo-polymer copolymer forms the PLA homocrystal. The L and D mixed copolymer forms stereocomplex crystal. With the crystallinity of these two elastomers, complex elastomer has a higher strength and modulus than the homocrystalline one. This shows the stereocomplex crystallization can reinforce the thermoplastic elastomer. We also use the stereocomplex crystallization to modify the physical performance of a supramolecular polymer. To prepare the supramolecular polymer, we first synthesize the hydroxyl-terminated low molecular weight PLA, PEG, PLA tree block. PEG is a soft block and it is a random copolymer of acid and butane. We then introduce the hydrogen bonding UPy group to the chain end. The UPy hydrogen bonding can extend the polymer chain and form the supramolecular polymer. For the tree block copolymer without without a UPy group, they can crystallize. This crystallization retards the macrophase separation of the tree block polymer. However, for the hydrogen bonding, for the tree block polymer containing the UPy hydrogen bonding unit, the hydrogen bonding UPy group destroys the crystallization of beta of PLA and PDLA chain due to the strong confinement effect of UPy group. The supramolecular polymer forms a layer structure through the macrophase separation. Then we mix the supramolecular block polymer containing PLA and PDLA block. For the supramolecular polymer containing only PLA and PDLA block, they are amorphous and can't crystallize. However, the polymer become crystallized in the mixture when PLA and PDLA are mixed. Block polymer are mixed. The crystallinity can be controlled by changing the mixing ratio of PLA and PDLA block. It increased as the content of PLA and PDLA block becomes similar. This indicates the stereocomplex crystallization has a higher crystallability than the homocrystallization in the same condition. The non-crystallizable material become highly crystalline material after stereocomplex crystallization. Due to the effect of crystallinity, stereocomplex crystallization has a remarkable effect on the mechanical and the thermal property of supramolecular polymer. The stress strain curve and the DMA curve show the strength, modulus, and the softening temperature of stereocomplex crystal improve with the crystallinity of stereocomplex crystallization. However, the polymer will become more brittle and its fracture strain decreased after stereocomplex crystallization. We further extend our study to the thermoset elastomer. In this case, we cross-linked the PLA, PLA tree block polymer by a cross-linker using the well-known polyurethane chemistry. The ratio of PLA and PDLA are controlled in the network. And the homocrystalline polyurethane network contains only PLA or PDLA block are non-crystallizable and transparent. However, the polyurethane containing both PLA and the PDLA block are crystalline and not transparent. X-ray diffraction result also confirm polyurethane change from the non-crystalline structure to the crystalline structure through the stereocomplex crystallization. And we also found the polyurethane elastomer shows the interesting thermal transition behavior in the DSC curve. We can see an additional melting peak above the transition of PLA. This is due to the melting of crystalline phase in the network. The glass transition and the metal phase melting give the material a broad thermal transition in this temperature range. We further use this broad phase transition to design the multiple shape memory material. For example, we can design the triple shape memory material for the homo-polyurethane. It was deformed at 90 degrees C and then cooled to 55 degrees C to fix the temporary shape. It was then deformed to the second temporary shape and fixed by cooling to the room temperature. The sample can recover to the first temporary shape and then to the permanent shape upon heating. Because the stereocomplex polyurethane has a much broader transition, thermal transition in this temperature range. We can design the more shapes and prepare the four-fold shape memory material for the stereocomplex polymer urethane. Except for the polymer elastomer, stereocomplex crystallization can also be used to tune the physical property of physical gel. For this study, we prepared the physical gel based on the amphiphilic graft copolymer. This copolymer was synthesized by the random copolymerization of PLA and PDLA macromolecules and isopropyl amide napalm. Then we change the solvent to water and prepare the hydrogel film. In this hydrogel, hydrophobic PLA and PDLA act as the physical cross-linking domain, which are surrounded by the hydrophilic polynapalm chain. We analyze the network structure by we can see a broad correlation peak in the SAXS profile. We can estimate the domain size by fitting this peak compared to the homo-crystallization physical gel. The stereocomplex hydrogel has higher density but smaller size of hydrophobic domain. This means the stereocomplex crystallization has a better physical cross-linking effect on the hydrogel. Therefore, the stereocomplex hydrogel is more rigid than the homo-hydrogel. It has a larger strength and modulus, but the lower flexibility. Stereocomplex hydrogel also has the better solvent resistance than the homo-gel. The homocrystalline gel a brick is a water ethanol solvent, mixed solvent at the high ethanol concentration. However, the stereocomplex hydrogel can sustain at the same condition. As we know, polynapalm is a thermo-responsive polymer. It is hydrophilic at low temperature and hydrophobic at high temperature. When we move the hydrogel from the cold water to the hot water, the water will dissolve and the hydrogel will shrink in the size. However, because the stereocomplex hydrogel has a strong physical network, its water desorption and shrinking was less obvious than the homocrystalline gel, using the different shrinking ability of Stereocomplex and homocrystalline gel. We prepare the bilayer actuator. One layer is a Stereocomplex gel. The other layer is a homocrystalline gel. The bilayer can change the shape. Reversibly in the cold water and hot water. And in the final part, I will talk about the use of Stereocomplex crystallization to control the polymer self-assembly in the dilute solution. As we know, amphiphilical polymer can assemble in the micelle in dilute solution. The most common structure is a co-shell micelle. The micelle part can aggregate into physical gel if we increase the polymer concentration or changing the solvent property. This self-assembly process is strongly related to the crystallization of the hydrophobic block. For example, for the block of copolymer micelle, if the micelle core is crystallized or co-crystallized, the micelle would have different size and stability. For the copolymer micelle in high solution, if the hydrophobic block are crystallized or co-crystallized, the micelle solution can form strong and dense physical cross-linking through the crystallization-driven chain exchange. The aggregated physical can different physical. And in this part, we first study the micelle formation and stability controlled by crystallization, Stereocomplex crystallization. We use a random graft copolymer of OEGMA and PLA or PDLA. This amphiphilical copolymer was prepared by ATRP from OEGMA and PLA or PDLA macromolecules through ATRP. We then prepare the micelle solution from the homocrystalline copolymer or the mixed copolymer containing PLA and PDLA. The copolymer can form micelle in dilute solution. However, the micelle size increased when the L copolymer and D copolymer are mixed. From the XRD plate of the freeze-dried micelle, we can see the mixed copolymer forms crystalline micelle because the Stereocomplex crystallization between PLA and PDLA block. Similar to the polynapalm, OEGMA is a soluble in water at low temperature, but insoluble at high temperature. So the synthesized graft copolymer are also thermo-responsive. The copolymer solution is transparent at a low temperature, but become turbid is correlated to the cloud point. It's interesting. The cloud point of copolymer solution can be controlled by the Stereocomplex crystallization through changing the mixing ratio of L copolymer and D copolymer. The homocrystalline copolymer shows a high cloud point, but the Stereocomplex copolymer has a low cloud point, even though they have the same concentration and the same copolymer composition. So we can control the cloud point in a wide range by changing the mixing ratio of L copolymer and D copolymer. We think the different thermal response sensitivity is related to the method structure. We analyze the method structure by solution SAXS. We use the Cochrane model to fit the SAXS profile and obtain the method structure such as the gyration radius, the aggregation number, the core radius, and the shell thickness. The aggregation number means how many copolymer chains associated in one micelle. From the SAXS analysis, we know the gyration radius, aggregation number, core radius of micelle increase after the stereocomplex crystallization. This means the stereocomplex crystallization between the L and D block can associate more copolymer chain in one micelle and lead to form the larger micelle. We further use the temperature variable SAXS to analyze the thermo-responsive mechanism of the copolymer micelle in solution. When the temperature is above the cloud point, we can see a correlation peak in the SAXS curve. This peak is related to the interaction between micelle particles. We use the sticky hard sphere model as a structure factor to analyze the distance and interaction strengths between the micelle particles. Intermicelle attraction force. We found the intermicelle attraction force increased after the stereocomplex crystallization. Based on the SAXS analysis, we can explain the stereocomplex, the thermo-responsive behavior of copolymer controlled by crystallization. Mixture, both L and D copolymer. Stereocomplex crystallization lead to form the larger micelle. Larger micelle will have stronger van der Waals attraction force between each other. So they can and show the lower cloud point. Except for the copolymer assembly, another solution assembly of polymer is the growth of crystal assembly or single crystal in solution. Because the stereocomplex crystallization and homocrystallization have the different mechanism. With crystallization, in polymerization, a unique assembly is a shish-kebab morphology. This shows the morphology of shish-kebab crystal. The central part is shish, and the kebab crystal grows on the surface of the shish. We use the stereocomplex crystallization to control the shish-kebab morphology. In this study, the fiber by electron spinning, and to use this electron spinning fiber as a shish, then we dip the fiber in the solution of PLA or PDLA home polymer or the PLA PDLA mixture to grow the shish crystal on the surface of the fiber. In both cases, we can obtain the shish kebab crystal. But the crystal morphology are very different in these two cases. In the case of the homopolymer solution, the growth of kebab is homocrystallization. We get the very big shish crystal with the loose packing. However, in the case of the PLA, PDLA mixed solution, the growth of the kebab is a stereocomplex crystallization. We get a very small shish crystal with a tight packing. The different morphology is related to the nucleation mechanism of stereocomplex and homocrystallization on the stereocomplex fiber. When the stereocomplex fiber was immersed in the PLA and PDLA mixed solution. Both the copper and the shishib are still complex crystal, and they have the good crystallographic matching. So there are many nucleation sites. This leads to growth of more copper crystal. However, when the stereocomplex fiber was immersed in the PLA or the PDLA homopolymer solution, there are few nucleation sites. This induces the growth of few copper crystal. And finally, I would like to give a brief summary for my talk. In summary, we have studied the crystallization kinetics, a process of stereocomplex polymer, which includes the formation kinetics, mechanism, polymorphic structure, and structure transition. Of course, this structure study needs advanced analysis techniques such as Synchrotron-radiation SAXS, solid-state MR. Based on this structure study, we establish the structure property relationship such as thermomechanical degradation, drug release property. Based on this structure property relationship, we also prepared several materials such as the micelle, physical gel, and elastomer. Our recent study are summarized in our recent review paper in Progress in Polymer Science. This review paper not only focuses on the co-crystallization, but also on the polymorphic crystallization of bio-based and biodegradable polymer. And finally, I would like to thank my graduate student who did this work. I also thank my collaborator, including Professor Chris Lee in Drexel University and Dr. Fujita in Liga, and several professors in ZGU. This work was financially supported by the Natural Science of China. I also thank the Shanghai Synchrotron-radiation facility for the WAXD and SAXS analysis. Most of all WAXD and SAXS analysis was done in these two beam lines. Thanks for your kind attention.